this is how to measure the distances to the stars.
What Friedrich Bessel did back in 1838 is he realised that as the Earth, here represented by point B, rotates around the Sun in the centre, it goes around anti-clockwise relative to the reference frame. At 6-month interval apart it's reached A, and he knew this distance here, which is the diameter of the Earth's orbit, had already been calculated. He noticed that some stars, particularly when he took photography or pictures of the night sky, appeared to show a tiny change in the movement on the maps, on the pictures, depending on when they were observed. So this particular star he was looking at showed this tiny jump in its position, and he measured the angle, this change in where the star, so the position of the star at this point when it was A, and the position of the star at point B. And the half of the angle ACB is the parallax of the star, that's the apparent jump. The easiest way to see this, if you look at a lamppost in your street, close one eye, it appears to move, but distant objects in the horizon don't. And the angle, 1 arc second, is 1/3600th of a degree, and that's a parsec would be a star which would give an angle of 1 arc second jump if observed from Earth. But the nearest star is further away from that. It shows a much smaller parallax. So the smaller the parallax, the further away the star is. And the nearest one we've got to Earth is called Proxima Centauri, and it's 0.763 arc seconds apparent jump. So that's the further distance away. So the smaller the value of the parallax, then that means the further away the star is. Using this method, you can calculate the distances to stars which are about 30 parsecs away, or in terms of light years, because a light year works out as being 3.26. Well, 1 parsec is 3.26 light years. So that gives you a way of measuring. And you can only, as I say, measure out to about 30 parsecs from Earth, and 1 parsec being the parallax of 1/3600 degree, and the nearest star we have is 0.763 arc seconds.
It was known at the time of Bessel in the 1830s that the diameter of the Earth's orbit was 300 million kilometers. It's a long distance, but in stellar terms that is not a long distance. But knowing this diameter and being able to measure the apparent movement of the star, in which case it was 61 Cygni. In actual fact, this was a pair of stars orbiting each other, and Bessel was even able to calculate the period of the stars and their orbit around each other, but he was really looking at how far the system was away from the Earth, this double star. It's in the constellation of Cygnus, or the Swan, only just visible to the naked eye, and he found this parallax, and basically he found the parallax was 0.35 arc seconds. Bearing in mind 1 arc second is 1/3600th of a degree. His parallax was just over a third of that. So that's a very small angle in which those pair of stars that are called 61 Cygni appear to there's an A and a B star appear to jump, if you like, against the background. And of course that works out as being around 11.4 light years away. So the Parsec Measurement, which works out that it's you can calculate 1 parsec as being 3.26 light years. The parsec itself basically was a means of measuring the distance. The distance being measured here, you want to measure the distance between you and this star. And of course the star itself was giving out light, and the idea of using a light year is it's telling you light year is the distance that light travels in a year, and it became a much more convenient means of measuring long distances to the stars. So in terms of light years, 61 Cygni, which is not the closest star to Earth or star system closest to Earth, it's 11.4 light years away. So when you look at that in the sky, you're looking at it as it was 11.4 years ago. If a star was further away than star C, which I'm supposedly representing as Proxima Centauri, the nearest star to Earth,
you're obviously wanting to measure the distance between you and the star, this distance from the star, light leaving the star and coming to you, then obviously the angle that you're going to have to measure will become smaller and smaller and smaller. So the smallest, well, the largest angle that you can measure is 0.763 arc seconds, and that works out as 4.27 light years away. So that means you observe that star Proxima Centauri as it was 4.2. Using a planetarium, I have a dial which rotates, and I set it on the date. I've set this one here to be 2100 hours. That's 9 o'clock to be February the 2nd. This particular planetarium works for latitudes of around 51.5 degrees north, works for Canada and Northern Europe, and it's a planisphere. And on this, once you set the dial, this shows you what stars will be visible. You can put the planetarium overhead, as you see my image in there, and you should be able to see that would be what would be in the sky. And you have to orientate it so that south would be where the actual planisphere sign is, okay, and you can see that south you've got the constellation of Orion, and you can also, it also has a dots going across it, and the yellow dot there is the position of where the ecliptic is in the sky, and that's where you're going to find the planets and the moon, okay, and also along the ecliptic you have the constellations of the zodiac, the so-called birth signs that people have. And if you say that you're a Pisces, that is supposed to mean that the sun was in that constellation as a the background of the constellation to that constellation when you were born, okay? And you can actually look for your own birth sign if you're interested in that. But these are good for a basis for starting astronomy, and I've used these a lot. But the basic idea is, if you place the planisphere overhead, match the planisphere pattern with the stars you can see if you don't know your north, south, east and west. And you can see on the side of it here it says eastern horizon, and on the other side your western horizon, okay? They're not fantastic. I mean, the idea is they give you the brightest stars and the shapes, and with the dial you can obviously factor in daylight saving time. So at the moment in the UK where I am, it's actually the clocks go back in autumn, and it's February the 1st now. It's only just come out of January. So here's that's a couple of ideas. You've got software, you can use that on an old Windows 98 computer here, and a planisphere. The magnitude system, that is the system by which we measure the apparent brightness of stars, and I'm not talking about the actual brightness of them, I mean how bright they appear to be from Earth, was first started by an ancient Greek astronomer called Hipparchus. Around about 150 BC, he looked at the brightest stars in the sky and he called them to be having a value of 1, and then the dimmest ones that he could see by naked eye astronomy, he gave them a value of 6, and in between he classified them, and roughly he found that the eye could discern a difference of brightness of about a factor of 2. Then later on, so basically by his system, if a star was 1, had a brightness of 1, that's the brightest he could observe, and one had a brightness of 2, that would be only half as bright. If one had a brightness of 3, it would be half as bright again as the one which was 2, or a quarter of bright as the one that's 1. So you can see it's what's known as a logarithmic scale. Later on, 1830, the astronomer John Herschel, then working from England, discovered that he could actually measure brightnesses using a device, and he found the actual gap between the brightness scale, the ancient brightness scale used by Hipparchus, was if you observed a star of magnitude 1 and then one of magnitude 6, the jump wasn't twice, it was 2.512. In other words, a star of magnitude 2 was 2.512 times less bright than one of magnitude 1. And the convenience is that the difference in brightness across magnitude 1 and 6 is 100 times, and so a star with a magnitude of 1 is 100 times brighter than a star with a magnitude of 6 using Herschel's more exact mathematical scale, logarithmic scale.
But the problem was, as Herschel found, there were stars in the sky that were brighter than magnitude 1 using the ancient system. For instance, you've got the star Vega, which has 0, and there's even one called Sirius, which is the brightest star we can observe in the northern hemisphere, has a magnitude of -1.4. And if you look at other objects in the sky besides stars, you'll find that the sun, as observed from the Earth, is 14,000 million times brighter than Sirius and weighs in at -26.8 on the apparent magnitude scale. When the moon is full, it's -12.5 apparent magnitude. And of course, notice I've used the term apparent magnitude. That is the brightness as observed from Earth. And as noted by ancient astronomers themselves, when they looked at this in medieval times, people realized that some stars may well appear to be bright only because they are close to us. It was only firstly using the parallax method that astronomers observed that some stars appear to move with respect to the background stars, depending on when you observe them, what time, what season you observe them from Earth, that people realised that the brightness depended on how close the stars were to us. But that magnitude scale is still used today. The thing to remember is the smaller the magnitude, the brighter the star. And it is a logarithmic scale. In other words, 2.512 times is the times by which you have to times the magnitude by to find if they're not so. The magnitude 2 is 2.512 times fainter than magnitude 1. So here's what the sky would look like if you had an eclipse of the sun, a total eclipse of the sun, and you were able to see some stars. But of course, at the moment, outside where I am in the UK, it's very cloudy, and the sun is up. But it shows you what objects are up there in the sky. It's a good learning thing to do during the daytime. If you want to learn some astronomy, it shows there is a moon. The moon's up in the sky there. There's various planets, and this uses ancient symbols for the planets. You can click on what the symbols mean. I know the one with the little arrow is Mars, and the one next to it there is Venus. And you have to be careful when you look at anything in the sky when the sun's up, because it can blind you. Some people have got telescopes, and if you've got the correct tracking mechanisms on your telescopes that track the actual hour angle, the right ascension, the declination, that is a plus and minus value, sort of vertical up and down, you can actually track planets in the blue sky. For instance, a planet like Venus, if you know where it is in the sky and you're aware of how to block the sunlight out, it can be observed. And these are other objects in the sky. This shows you where the sun is in the sky at the moment, that circle there with the dot in it. Still quite low, obviously, because the ecliptic, that is the great circle across the sky where the sun, the moon, the planets, and also, of course, at night time the stars, which form the so-called zodiac signs. This area of the sky in the winter time, which is the moment in February in the UK, is at its lowest, and your observing angle from the Earth to the heavens changes. This ecliptic changes according to the seasons as you view them from the Earth. And if you'd see my video about how sundials work, you'll see what I mean. But if we were able to see the stars at this time of the day, this shows you what stars would be visible. Now, the idea of using these computer programs is brilliant, and you can get much more updated ones than this one. But this is how I started really getting interested in astronomy, because I looked at these basic software programs, and I was able to match them up with what was in the sky. If I want to set this sky map I've got here from Windows 98 to this evening, currently it's what's in the sky at the moment, but as I said earlier, the sun's out, so you can't see this, but it is what's up in the sky. If I want to set it for a time when it's night time, I can factor in the time that this is for 9 o'clock tonight, but I've also told the program that you have to add a correction because of the daylight saving time. I basically then take the mouse button and I click on OK, and it'll change. There you go, you see. Now I've got a map which it looks exactly like my planisphere map, but much more detailed. This goes down to about magnitude 5, and the magnitude scale on stars is logarithmic. It's basically
it doesn't mean that one is you know, it's not an exact scale as regards scalar. You know, one's twice as bright as the other, whatever. It is logarithmic, so you have to make calculations based on the fact that magnitude was a way of compressing the massive changes in brightness into a scale, which is a logarithmic scale. So basically, some stars are so bright they even have negative magnitudes. Okay, and that way you can encompass huge changes in brightness. You can look at this one here. This is very prominent where I am in the sky. That's Gemini, so-called the twins. Okay, and obviously Orion. Most people are familiar with the belt of Orion they see in the sky. You'll see some in my star pictures, and also the very unstable star at the top there, Betelgeuse, and also another constellation there which is called Taurus, or the Bull. You may have seen that in the sky. And of course, along the ecliptic, which is here shown, you've got your constellation of the zodiac. I can see there's Cancer. I've looked at an object there called Parsec, or the Beehive Cluster, and coming along there you've got Canis Minor. That's the small dog. And Gemini, of course, is a birth sign. Taurus, and there's another one here, Aries as well, and that's what's visible in the sky at the moment. And it's also handy because it gets you familiar with the night sky. That's the first thing to do I'd recommend if you're interested in astronomy. Using the speed of light as a means of measuring distance, and remember a light year is the distance light travels in 1 year, means that when you view the moon in the sky, you don't view the moon as it is exactly. You view the moon as it was 1.3 seconds ago, because that's the time it takes light for travel from the moon to Earth. And the sun, when you look at, well, you should never look at the sun anyway, because it can blind you, but the sunlight, when it reaches you, has taken 8.3 minutes to reach you. The nearest star to us is called Proxima Centauri, which is observable in the southern hemisphere. And you observe that star as it was 4 years ago, so that gives you an idea of stellar distances. Using this very simple planetarium, which is called SkyMap 2, which I bought some years ago, and I can also identify stars down to about magnitude 5, and as I explained earlier, the larger the number of the magnitude, the fainter the star. And this will tell me, for instance, this is one I'm looking at, which is in Pegasus, which would be up in the sky if I could see the stars at the moment. Of course, if you have a total eclipse of the sun, that is where you have a new moon that blocks out the light from the sun to Earth, then stars do become visible. This is what's up there in the heavens at the moment. This tells me that a star I've clicked on, it gives you its proper name. It gives it something called a Bayer letter, its Flamsteed number, its magnitude, it's 2.9, and its position in the sky, its right ascension in terms of hours and minutes and seconds, and its altitude or its declination. When you have a telescope, you have to set these right ascension and declination angles, if you like, an hour angle, in the way that the sun and the stars appear to move around the Earth. And remember that the Earth... To tell the difference between sidereal time, which is star time, and solar time, let's look at what happens if you have a sun, such as this one here. So this would be a star, which would be another planet's sun. And here we have a planet here. And on this particular planet, which was the golf ball, there's a tick on it anyway, and I've put a circle around. This represents an observer where the tick is. At this particular point, this planet is facing the sun, and it's high noon. Now, in this particular planet, for the purposes of this demonstration, it doesn't actually rotate on its own axis. So this particular planet is not rotating as the Earth does. If you imagine the Earth rotates on its own axis, as we know, in 24 hours, okay, which is our time for a day. It's not exactly 24 hours, as you know, but let's see what happens if a planet doesn't rotate on its own axis, but still goes around its star, in this case the sun, without actually rotating on its own axis. Well, here we go. We start off, say, we're rotating around anti-clockwise. Now I'm always facing the same part of the journey, going around the star.
Now what you can see is if you were the observer, already we start off being noon, it's becoming evening time, okay? Now I'm getting just glancing rays of my star from here onto where I am where the tick is, and by the time I'm getting to this part of my orbit, even though I'm not rotating, always facing the same point, I'm now slowly going into night time. Definitely there's that star here which stays in the same position in this example, it's setting, and by the time it's rotated around to this part of its orbit here, right, it's completely midnight if you were where the tick is, okay? Carry on with the rotation. I'll just move my arms like that, and as I'm carrying on, it's becoming late night time now, and slowly where the tick is, you'll start to see the sun rise, okay, and it'll get higher and higher in the sky, okay, and then eventually as we come back here, the star will appear to be higher and higher in the sky, so you're looking from where the tick is. When you've gone a full orbit right round this star, you're back to where you started. But what you should notice is that you've had a sunrise and a sunset without this particular planet even rotating on its own axis. Now that's a difference between solar time and stellar time. Stellar time is what we call sidereal time, and it adds an extra day on. So the year, as regards to the stars, is 366.25 days. With regards to you turning on your axis, if you were the Earth, it's 365.25 days. So by travelling, just by going once around a star, you add a day on. So the clock that runs to star time runs faster than the clock that runs to solar time. And you can see this by the fact that stars appear to rise 4 minutes earlier every day. So at night time, the same star you'll be looking at 9 o'clock will have already been advanced into the sky 4 minutes further along.